Okay, so this is our first lecture. Um, let's discuss first what the purpose of this class is. The main idea is to uh, reconstruct all the ideas and facts that you learned in basically Calculus 1, reconstruct them rigorously based on some initial assumptions that you make about numbers. And then, so those assumptions that we're going to call axioms and what follows. And based on those assumptions, you want to define various notions of calculus, things like continuity, derivative, integral, and so on. And you want to do this in a logically consistent, what is called rigorous way, where all these facts are derived from axioms by constructing proofs and proving the facts that are known, things that are known as theorems. So theorems are going to follow from axioms just based on logical arguments. Uh, since we're going to be, throughout this course, we're going to be dealing with numbers, eventually real numbers, what we need to do is to develop the logically consistent underpinning of what we understand by numbers. And I'm going to do this more or less systematically, starting from the simplest numbers that we know, and then building up towards real numbers. And once we establish property of real numbers, then we will continue towards calculus. So the simplest type of numbers, right, that we can think of are natural or counting numbers. And in fact, the developments that I'm going to follow here regarding numbers are in some sense historical. So initially people learn how to count. And then as civilization progressed, as certain needs developed, more and more elaborate notions of numbers were developed. But in the beginning there, you have natural or counting numbers. And so what want to do with them, I want to follow the same strategy as I just outlined. What we would like to do is to understand what is the least uh, amount of information that we have to assume about natural numbers so that everything else about natural numbers can be established based on those initial assumptions. And let's think what sort of properties of natural numbers or counting numbers do we expect. So if you count, then obviously you'll count 1, 2, 3, 4, 5, 6, and so on. So the smallest counting number that you can have is 1, right? So you can have one object or you have more. So that means that your system of counting numbers must contain 1 in it. That's number one. Number two, if you count, you should be able to continue. The more objects you have, the larger counting number you will need. And in fact, the number of objects should not be limited. So you should be able to, in a sense, count all the way up to infinity, which means that given any counting number, I should be able to move on to the next counting number. So given any counting number, there is a larger counting number that in our terminology that we're going to use here, we're going to call a successor. So you would expect that any counting number has a successor. Okay, so that is the second thing that we expect. The third thing that we would expect is that if we have two numbers and they have the same successor, then clearly both of those numbers must be the same. So two numbers having exactly the same successor should imply that both numbers are the same. I should not be able to have 5 after 1 and after 3, right? Because numbers should follow in a sequence. So that's the third fact. The fourth fact is this, that if I count, it should not be true that my counting will branch off at a certain number. So it cannot be true that, for example, number 5 will have two successors. It cannot be true that both 6 and 7, for example, are after 5. So that means that each number has a successor and each number has a unique successor. There is only one successor to every counting number. One other fact is that 1 is the least counting number. There is nothing less than 1. So therefore, there is no counting number for which 1 is a next number. So 1 cannot be a successor to any counting number. So this is a set of properties that we expect that I'm outlining in these paragraphs that you can read in more details about. So once we think about all these properties that we do expect, then we can formulate them, as I said, in a set of axioms that you are assuming, that you will assume that they're sort of God-given and they're true. And so to summarize the properties that we just discussed, we have the following 5 axioms. Number one, 1 is, and by the way, the set of natural numbers we're going to denote, you probably have seen this before, we're going to denote by boldface letter N. So the first property, first axiom is 1 is a natural number, so 1 belongs to the set of all natural numbers. Then if a number n is a natural number, then n plus 1, its successor, is also a natural number. Like we said, 1 is the smallest natural number, so 1 is not a successor of any natural number whatsoever. If the set of natural numbers cannot have two branches converging at the same point, so if n and m have the same successor, then n and m clearly must be the same. And then also the set of natural numbers cannot branch at some point, so you cannot follow one chain of natural numbers and then totally independent chain of natural numbers that have nothing to do with each other. What this means is that if 1 belongs to the set of natural numbers, let me back up a little bit. So if I have a set S, which is a subset of a set of all natural numbers, and such that that set contains 1, and also the set satisfies a property if a natural number is an S, then its successor is also an S. What should we expect? What should we expect from a set S like this? So if 1 belongs to S, and for any n and S, n plus 1 is an S. If 1 is an S, then that means that 2 is an S. But if 2 is an S, then from here, 3 is an S. If 3 is an S, then 4 is an S, and so on. And so that means that we would expect that that S actually should contain all natural numbers. And so that's a statement of this fifth axiom, that if I follow all natural numbers in a sequence, then I'm going to recover the entire set of natural numbers. Like I said, the natural numbers cannot branch off at some point. And we're not going to prove that here, but all of these five axioms actually are sufficient to derive all the properties of natural numbers that you can think of. So this is sort of a minimal set of properties of natural numbers that you need to understand what natural numbers are. Okay, so uh, then from now on, we identify a set of natural numbers with a set that satisfies these five properties, five axioms on the screen in front of you. Okay, so let's see what sort of things we can do with this set of axioms if we will be able to derive any useful properties from those. And before we do that, let me introduce the following notation that I'm going to use throughout the course. Basically, the notation that you see here, this means that A belongs to S if you have the same symbol, but it's crossed by a line. That means that A is not an element of S. A similar symbol, but without a line. So if this looks like an E without a middle line, that means that I have two sets, S and T, and S is an element. S is a subset of T. What it means for S to be a subset of T, every element of S is in T, but T in principle can have more elements than S. This symbol simply means for any, so for any number A in a set S. This symbol means that there exists an element A of S that will satisfy some property. The column means sometimes means words such that. And so why do we need this notation is so that it's much easier to write out the proofs later on because you don't need as many words to do this. All right, so with this notation, now I can rewrite the fifth axiom, the most complicated axiom from above. Let me remind you what it was. So if S is a subset of N that satisfies two conditions like this, then S must be the same thing as N itself. And so let's see, how can we write this down? We have S, which is a subset of N, and it satisfies two properties. One belongs to S, and if N belongs to S, then N plus 1, then N plus 1 belongs to S. And those two properties imply that S is actually equal to N. So you see, it takes much less space to express the same statement by using these symbols. Okay, so one other example is that if I want to describe infinite sets, right? So the typical way to do it is to list the elements of a set in brackets. But in this case, because if you have infinitely many elements, then of course you cannot really list them all. So rather than listing elements, we can specify a rule according to which we do include elements in the set. So for instance, if I want to describe some set A, which contains all even counting numbers, I can describe it as follows. So A is defined as a set, so the parentheses in this case mean that what I'm describing is a set. So this set consists of all natural numbers such that there exists another natural number, so k in n, such that n is equal to my n that belongs to the set A, that n is equal to twice that number, that natural number k. And if you think about it, then clearly this means that n must be even, and every even number can be described this way as 2 times some other natural number. So A must contain all even uh, counting numbers and not odd. So that's a way to use this notation to describe the set A. All right, so one application of the axioms that I mentioned above is something called the method of mathematical induction. And the method of mathematical induction basically allows you to prove that infinitely many statements that you have are actually all true. So, let's suppose that somebody gave us a list of infinitely many statements, which I'm going to denote by P1, P2, P3, etc. So I have a statement Pn, where n ranges from 1 to infinity. So P has an index, and that index is a counting number because I can count my statements. Some of those statements may be true, some of those statements might be false. So maybe, for example, the statement P1, use a different color, P1 might be 2 is greater than 1, P2 is greater than 2, P3 is 4 is greater than 3, so then Pn is n plus 1 is greater than n, and n can continue all the way to infinity. Obviously, all of these statements are true, right? There is nothing to prove here. Uh, Everything, all infinitely many statements are true. Let's look at the second example. So let's say the statement P1 here is 1 is divisible by 2. That is certainly false. P2, 2 is divisible by 2. True. 3, P3, 3 is divisible by 2. False. Pn, n is divisible by 2. And that may or may not be true. So every other statement in this case, whenever n is an even number, the statement is true. When n is an odd number, the statement is not true. So once again, there is not really much to do here. It's clear what is true and what is false. Okay, let's look at the third example. Let's say the statement P1, statements P1, P2, and P3 are as I wrote them on the screen. So the first statement is 1 plus 2, 3 on the left side, equal to 2 times 3 over 2, which is also 3, right? So this statement P1 is true. The second statement, 1 plus 2 plus 3, that is 6. 3 times 4 over 2, 12 over 2, 6. So P2 is true. Now P3, 1 plus 2 plus 3 plus 4, that's 10. And 4 times 5 is divided by 2, 20 over 2, also 10. So P3 is true. So that means that the first three statements here are true. Now, what is the nth statement if I follow the same pattern? So at the nth level, then, I have to add first n integers, n positive integers. Then I claim, just looking at the pattern, that this must be the same as n, right? So here, 2, 2, 3, 3, 3, 4, 4, and then the second integer is always one larger. So the statement Pn is then as follows. And now if I look at the statement Pn, it's no longer as easy to show that it's true, right? Because how exactly am I going to do it? And also I have infinitely many statements like this. So if, for example, n is equal to a million, to show that this is true, I'll have to add million numbers on the left-hand side, and then somehow demonstrate that this is equal to million times million plus 1 divided by 2. So what we want to divide some sort of a procedure which will easily enable, which will enable us to easily demonstrate that all of these statements are true by proving certain easy facts. And that is going to be this mathematical induction that I mentioned. And so let's now figure out what it is and why it is true. So let's suppose again that I have infinitely many statements. Some are true, some are false. Each statement has an index, right? They're all indexed. What I'm going to do is I'm going to consider the set that I'm going to define or denote by S, and a set S is going to consist of indices of all statements that are true. So for example, if out of my infinitely many statements only P1, P7, and P531 are true, that means that the set S consists of integers 1, 7, and 531. And so that means that S must be a subset of a set of natural numbers because S is a set of indices of true statements. So it's a set of indices, set of numbers. All right, so now suppose that we have the following, that we know somehow that we're able to show that P1, the first statement in on our set of infinitely many statements, P1 is true. And number two, suppose that we are able to show that whenever the statement Pn is true, then the statement Pn plus 1 is true. Now, let's try to rephrase that in terms of our set S. S consists of indices of all true statements. So if P1 is true, that means that 1 must be an S because S consists of all indices of true statements. Then if Pn is true, that means that n is also an S, right? Because the index of a true statement is an S. But if it follows that Pn plus 1 is true, from the fact that Pn is true, then I can rephrase that in the following way. If n is an S, then it must be true that n plus 1 is an S. Well, but then we can compare this to the axiom number 5. So axiom number 5 said this. So in our new notation, if 1 is an S and n is an S implying n plus 1 is an S, then S must be equal to the set of all natural numbers. Well, but that's exactly the same thing as of what I have written here. So my S satisfies the conditions of axiom number 5, and then from axiom number 5, it follows that S must be equal to n. So S consists of all natural numbers, which means that the statements Pn are true for all indices n. So that means that all of my infinitely many statements are true. So then the mathematical induction can be summarized in the following way. Let's suppose that again we have a set of infinitely many statements, and we know that the first statement is true. This will be called basis of induction. And then suppose also we know that if the statement Pn is true, then Pn plus 1 is true. That would be induction step. If we know both of these facts, then from what we just obtained, right, from axiom number 5, this implies that Pn must be true for all n. So all infinitely many statements are true. Okay, so let's now try to apply this mathematical induction idea to this example that I showed you previously. I want to demonstrate that the sum of all integers up to n must be the same as n times n plus 1 over 2. And this should be true for all n. And I want to use induction. Okay, so then what is basis of induction? Basis of induction is to demonstrate that P1 is true. What is P1 in this case? So P1, I'm only adding 1. So on the left side, I have 1. And on the right side, n is 1. So that means I get 1 times 1 plus 1, 2 over 2. That is also 1. So P1 is true. So basis of induction holds here. It's true. Typically, a slightly more difficult thing is to uh, prove the induction step. So let's see how it works here. I'm going to suppose that Pn is true. Now, what is Pn? Pn is this statement. So I'm assuming it is true, and I want to show that if this is true, then Pn plus 1 is true. So who is Pn plus 1? Pn plus 1 is exactly the same statement as is circled on the screen, except that I should go to up to the next integer after n, which is n plus 1. So then the statement n plus Pn plus 1 is add up all integers up to n plus 1, and this must be equal to n plus 1 times n plus 1 plus 1 over 2. So at this stage, I don't know if this is true, but I do know that the previous n statement is true. And I have to use the n statement to demonstrate n plus first statement. Okay, so what do? We just look at the left-hand side of Pn plus 1. So we have to add all terms up to all integers up to n plus 1. But because I'm doing addition, I can add separately first n terms. But adding first n terms, because the statement Pn is true, means that I'm going to get n times n plus 1 over 2. So that means that this sum I can rewrite as a sum of the first n terms, right? It is given by this formula, plus this additional n plus first term. Then I have a common factor of n plus 1 in both. I can factor it out. I have n over 2 plus 1 left, which is the same thing as n plus 2 over 2, which is the same thing as this. And that expression is exactly the same as what I have on the left-hand side. So that means that Pn plus 1 is true. So from Pn being true, it follows that Pn plus 1 is true. So that means that the induction step holds. So both basis of induction and induction steps, an induction step is true for this formula, and so that means that this formula holds for all values of n. So it is actually something that we're going to use in the future for those of you who will take the second semester in integration, for example. We'll need these kind of formulas to compute some elementary integrals. So this is all for this lecture. In the next lecture, I will start by doing more examples of induction, and then we'll move on to rational numbers.